Myself and Dino Adikaram will be presenting today. We will be recording this session, so please turn off your camera or rename yourself if this is of concern to you. I'd also like to acknowledge the traditional owners of the lands on which we operate, the owners being the people of the Yalukit Willam of the Boon Wurrung country that makes up the Greater Kulin Nation. Dino and I are both chemical engineers, with Dino also having a double degree in biotech. We have received questions as part of the enrolment or the sign-in process, which we will answer at the end of the presentation if there's anything that's not covered. But if there's something else that comes to mind during the session, please don't hesitate to drop it into the chat area as it comes to mind.
Right. Welcome everyone, my name's Dino Adikaram. So at Solve, we run a direct-fired thermal desorption plant. We're part of the Enviropacific company as our main company. Solve is just the name given to the plant. So we're based in Altona, Victoria, which for those that don't know is 20 minutes west of Melbourne's CBD, and we're located on a heavy industrial site. We lease land off the Dow Chemical Company, and we're surrounded by the likes of Qenos, BASF, and the mobile refineries just up the road from where we are as well. So we were EPA licensed as of 2018, but the story started a lot earlier in 2015, where we had to start getting permits and approvals from the council, the EPA, etc. So as a company, Enviropacific specialises in thermal treatment. This is our fourth thermal desorption plant there that we own and operate. However, it is the first fixed facility. So the facilities prior to this have all been project-based, where it'd be set up for 50 to 100,000 tonnes of material to be remediated and then packed up and then sent off for its next use. Through the Solve facility, we've treated over 150,000 tonnes of material to date, and this also means that we've diverted about 150,000 tonnes of hazardous waste from going into a landfill. In terms of the process, I'll go through in a bit more detail in a future slide. However, in a quick explanation, the thermal desorption plant works by heating up a solid that desorbs the contaminants out into the gas phase, which gets destroyed, and then you're left with a solid that's free from any organic contaminants, and that can be reused. Over to you, Amy. Mute those.
Thanks. And just to that, we have continued to operate our site throughout all of the lockdowns, and we have received material from each of these dot points across Australia. PFAS. So PFAS is a very broad church, and it's an acronym for a class of fluorinated organic compounds. There's over 3,000 of these, and there's a handful that are in commercial use or have been in commercial use. Of these 3,000 PFAS chemicals, the longer chain chemicals have found to be the most problematic and are what come to mind as being the problem or forever chemicals that are discussed in the media. These long chain PFAS are very soluble in water, but they are also very stable. There is a bit of a trend for a lot of man-made chemicals, or many man-made chemicals, that over time they can degrade or partially degrade, and this is not the case with the PFAS family. They were an accidental discovery by scientists who were looking to understand adhesives and non-adhesives, and found this amazing product that had water repellent properties, was able to be used as a coating on cookware to stop things sticking. It was great for suppressing fires, and so was used broadly in many firefighting applications, in stations, in helicopters, deployment and the like. It was also very successful in being included in household materials such as sofas and mattresses and household fabrics, which allowed household fires to start to become a thing of the past. This broad production and broad use of PFAS has meant that there is PFAS in many parts of our environment now through the production, the use, or when it is passed on to disposal. And so in entering the environment, it's taken up into the water, into plants, and into animals. PFAS really came to the fore as a consequence of one of its manufacturing sites in America. Adjacent to this production site was a farm that had been farmed for food, livestock for quite some time, and he had noticed that his cows that he was raising had started to become ill, and had started to investigate a little further and discovered that what was causing his animals to be sick was they had been eating food, drinking water, which had been the recipient of a lot of wastes associated with the local PFAS production plant. It took some time for this person to be able to collect the information, and it was this time, it was getting access to some pretty private and confidential information, and the mass lawsuit concept that made this quite a landmark case in America, and certainly for the multinational chemical manufacturers around the world. There are two movies that have been based on it. It's quite sensational. There's the Aaron Brockovich approach, or there's another one which is a little bit more technically correct called Dark Waters. It's not exactly the most uplifting information to be watching for entertainment, but through these investigations, this is where they discovered that the long chain PFAS was the problem. It's not restricted to America. In Australia, we have produced our own and imported across these product streams. So we now also experience PFAS in our waterways and in our vegetation and in our landfill, in our infrastructure projects is where it starts to become a major impact. And it's not just on Westgate Tunnel. It's also been identified in the silts of the Sydney Harbour, which is starting to influence how affordable, practical, and what are the options to putting in another tunnel under Sydney Harbour.
Right, so as Amy touched on earlier, PFAS was used in so many different formats. So we now see it in many different types of media. It can be found in PFAS impacted groundwater and surface water, and as a result, you see it in your sludge or your spent media, see GAC, for example. We see it in PFAS concentrate form, in impacted solids such as soils and NDD waste. It's in biosolids, and we also find it in concrete nowadays as well. So each of these material streams have different responses, and depending on your desire to either eliminate the risk or to just lower the risk, you can take a number of approaches. So if we dive into PFAS impacted groundwater and surface water, Enviropacific, for example, can do a water treatment plant, and the water produced as part of the treatment system is potable drinking water. So it completely separates the PFAS, and then what's created is a sludge or a spent GAC where the material is concentrated in. So this spent media actually needs a disposal pathway as well. So it can either go straight to a landfill, or it can go in for chemical immobilization or for thermal treatment. With chemical immobilization, it can go into a landfill, or it can go on an on-site containment cell, or it can also be reused. But then with thermal treatment, all the material is able to be reused, and the risk of the PFAS sitting there is completely eliminated. For PFAS concentrates, we've found that the most cost-effective solution is to send this in for thermal treatment. It's a bit strenuous on water treatment systems. For PFAS impacted soils and NDDs, again, you've got the option here of either immobilizing on site if you are content with lowering your PFAS risk, but if you want to completely eliminate it, and depending on the concentrations that you have, thermal treatment becomes a viable alternative. In terms of pricing, it's quite similar. as well. So PFAS impacted biosolids is also something that we're seeing a lot more prevalent these days with water authorities. Again, this can either be chemically immobilized or can be sent for thermal treatment itself. And then finally, impacted concretes with PFAS. So PFAS is very mobile and concrete is quite porous. So we found that the concrete is readily absorbing the PFAS. This concrete gets crushed at Solve and thermally treated, and we've been able to reuse this concrete as well. So PFAS treatment at Solve. So when Solve first went down the path of getting approvals to operate, PFAS wasn't even a contaminant of concern and one that people hadn't even heard about. The facility was designed to treat contaminated soils, but has since evolved to treat other, like a wider range of materials, which includes PFAS. So PFAS being everywhere and so apparent, we've had to go through field trials to have a look at the effect of thermal on the different forms that it comes in. And what we can say is at Solve, we've successfully demonstrated that the handling, the treatment, and the validation of PFAS through the thermal plant is completely successful. So if we go into the thermal process in a bit more detail now, we're able to separate the process into two paths, the soil path and the gas path. So if we start with the soil phase, basically in our pre-treatment building, the PTB there, we crush, screen, blend material to get it ready for treatment. From there, the loader you see there will hop the material into what we call our hopper, and then that will go into our rotary dryer. So what this is doing is it's treating contaminated soils or solids at a rate of 35 tonne an hour up to. And what it's doing in here is it's sitting rotating at 7 to 8 RPMs, and the soil's heating up to 550 degrees Celsius. And what this is doing is it's desorbing the organic contaminants out of the solid matrix. So the soils and other solids will sit in here for up to 15 minutes, 10 to 15 generally, depending on the concentration. And then basically we use treated water from our wastewater treatment plant, where we use a pug mill to rehydrate and cool this soil. And then we convey it into our treated soil building, where it undergoes testing and further validation to confirm that it's clean before it goes off for its next use. So the brains behind the operation is actually in the gas path. You've now got the soil that's completely clean, but what's happened now is that the contaminants in the soil or the solid are now in a gas phase. So these contaminated gases are taken through some ducting, through a cyclone as well. And what that does is it drops out the dust and the gas fragments. So the dust goes into the treated soil pathways, and the gases are taken into what we call the thermal oxidizer. The oxidizer heats the contaminated gases further up to 1100 degrees, and what that's doing is it's completely destroying the contaminants back to its trace forms. We then go through 2 stages of heat exchangers. 2 reasons for that. The next stage with the yellow scaffolding around is the pug mill, the bag house. That has a number of fabric filter bags. If the temperature's too hot, they catch on fire, which is not good. And the second reason is also because of the formation of dioxins and furans through the de novo synthesis phenomenon. By quenching this gas down from 1100 down to 200, you stop the formation of that. The next stage is the bag house. The bag house is there to filter the minute particulates that are in the gas phase, up to 75 micron. And then the next stage is to scrub any acid gases in the gas stream using a liquid scrubber, a packed bed scrubber. So basically the acid gases rise from the bottom. We use caustic to neutralize from about halfway, and we neutralize this gas as it leaves. So what's produced from our stack is predominantly carbon dioxide and water in steam. So we've got a continuous emissions monitoring system that's 24/7 online as well. So if there are, it's all hardwired into our control room, and it's set at 70% of what our license conditions are. So if gets even close to what our license is, it tells the control room, do something about it, reduce feed, stop feed, whatever you have to do. If it gets to a high level, it will stop the plant. Yeah, so that's how the plant works. In terms of chemical reactions, and if we talk about PFAS here, there's three main isomers of the molecule that the EPA heavily regulates. So it's the PFAS, the PFOA, and the PFH excess. So all these isomers are pretty similar in terms of their chemical composition. And then once you hit that with thermal desorption, what gets produced is carbon dioxide, hydrofluoric acid, and water. So hydrofluoric acid is a nasty chemical, but it's sent through the packed bed scrubber through the process and neutralized with caustic, which is sodium hydroxide. What this does is it converts the hydrogen fluoride into a harmless inert salt called sodium fluoride. We actually flocculate this out in the wastewater treatment plant as a harmless inert salt. So essentially what you've done is you've taken a nasty PFAS molecule, and by the end of the process, what you're left with is a salt. So that's how we deal with PFAS.
So the field trials that we have completed on site are really for us to get a better understanding of how those materials interface with our materials handling processes. We know that once the material is presented to the thermal treatment pathway, it can make its way through and will be successfully destroyed. So the broader range of media that we have received and processed to date has included spent resins and ion exchange resins from a very large range of different water treatment plants. We get soil is our main volume that we treat, and soil again is a very broad definition. That's any building materials, construction materials, anything that was originally from the ground tends to make its way into soil, being also concrete, bricks, tiles, and being that a lot of contamination is from brownfield site, we also get scraps of timber, some metal, and any other bits and pieces that you might normally find with an excavation of a brownfield site. Hence the reason why we do spend so much time pre-treating and sifting to ensure we can remove those items. Firefighting testing, training, and actual events means that there are PFAS concentrates in a liquid form that also make its way to site, and it can be introduced to a soil host to make its way through the thermal treatment plants. And we have also received biosolids. And again, it's about understanding how do we combine it with what materials so it can make its way through the material handling equipment that we have on site. What we have found from these trials is that regardless of what that host media is, once the PFAS is in the gas stream, we know that we can successfully destroy it in the oxidizer. The sampling that is taken in the treated soil building is taken off-site and tested by a third party, and the destruction efficiency has been found to be 99.99%, and this is a limitation of the testing equipment and methodology. But the EPA has issued an interim statement saying that this is deemed to be PFAS-free material if this is the final result, which is pretty awesome. So once people have found PFAS on their project site, we'd like to think that the next couple of steps can be resolved in consultation with the tools and services that we're able to offer at Enviropacific. That can be from winning the material and helping contain it on site, recovering it, transporting it. Of course, others can do that. We have received material from every mainland state of Australia, so we understand how to navigate the different state regulators in taking material across borders. We have all our material runs over a third-party certified weighbridge. It is stored in an environmentally controlled system. Our pre-treatment can take more than one attempt to get it right because we get such a variety of materials and we are the end of the line. So we have to make it work, and we've got many people who understand how to blend, treat and change the materials to come together so it will work from a materials handling perspective. Our treatment is verified to be effective because of some of the minimums that we have in place around operating temperatures, maximums that we have around emissions monitoring, and all the material that comes into the treated material shed is sampled and sent off-site for testing before it is then able to be classified and then taken off-site for either reuse or some people want to use it for incorporation into some structures as well. All of the volume that we have received and treated on site make us quite comfortable to be able to issue a certificate of destruction. And given the importance that people would place on such a certificate, we like to issue those once we have received the verification that that sample or that material that has been received has passed through the system and has landed in the treated material shed. So at the moment, we have a broad range of materials that we can receive for thermal treatment, and it's not just PFAS, it is often found with co-contaminants, and this is another factor that is considered as part of the blending process. And we are partway through the installation of a drill mud plant on site, so I think they've just stopped for lunch, hence there's not much noise at the moment, but in a couple of months we will be receiving non-destructive drill muds also for washing. We can take dirty drill muds for receipt, washing and treatment. We'll now start to move into some of the questions that we've received during the sign up or online. One of the questions was around about PFAS slurry. Depending on how what the liquid solids combination is at the moment, we can receive some slurries, and in the future, once the NDD plant is up and running, we'll be able to receive a PFAS slurry which is more liquid than solid for the current arrangement. There's a question here about the cost, or the question just comparing off-site disposal compared to on-site immobilisation. Dino, do you want to have a talk to that one?
Yeah, for sure. So off-site disposal, such as sending it to a thermal plant compared to on-site immobilisation, from a cost point of view, it's quite comparative. The difference there is obviously having to transport the waste or versus the actual desire to eliminate the PFAS risk or to just lower it by immobilising. So it really depends on your desire. But from a, I guess, commercial point of view, it's quite similar. There is a bit of a difference from the risk elimination point of view.
I can see there's a bit of a conversation happening online around can PFAS make its way into asphalts? And look, it's absolutely right. Water can permeate into rocks. And this is a bit of a real life experience that we have at the moment. Dino mentioned that we are on an industrial site. There is legacy contamination here, including PFAS, and that PFAS has been found to have made its way into quite large rocks. So wherever water goes, the PFAS tends to follow. It's just that the water can continue to move its way through and the PFAS will get left behind. We've had some questions around what are some options for long-term remediation measures. Long-term remediation, I guess it says this distinguishment between immobilisation or destruction. It's not really any other items or options in between the two. Any other treatment technologies for on-site or on projects? You've got some options to talk through there, Dino.
Yeah, so I guess if you've got it on a site and we're assuming that it's a solid where the PFAS is in. So like I mentioned earlier, it can be chemically immobilised and sent off-site into a landfill, or it can be immobilised and kept on site in a cell. Or the other option is to send it off for thermal treatment and destruction.
Thank you for that. I'm not seeing any more questions come up, and I think between these follow-up questions and the presentation content, we've managed to get through some of the areas that were causing concern to all of us around PFAS. Thanks for joining us today. If you do have anything else to ask about, you will get a very short follow-up email from us, which will essentially be this last slide. Please shout out if there's something a problem we can help out with. PFAS or broader contamination, any of that's right up our alley. Enjoy your week.
Thanks, everyone.